Our next speaker is Vera Hur. She's from Urbana-Champaign. She is going to talk about the Benjamin-Feir instability.
Thank you, Mark. And thanks for the organizers for the invitation. It's nice to be here. All right, this is a joint work with Jared Bronski at my university and Matt Johnson at Kansas. The departure point of this project is, are there stable periodic traveling waves on the surface of water? And the answer seems yes, if we accept a proof by photograph. Okay, for example, by the way, this is a famous photograph of Stokes waves that appeared in the National Geography in 1933. But the story is more complicated than just a single photograph, so let's look into it. Stokes is probably among the first who thought about these waves, which are periodic and traveling in a constant speed without changing form at the surface of traditionally two-dimensional and infinitely deep and irrotational water flow and acted only by gravity. We call these waves now Stokes waves. Stokes argued that these waves behave quite differently from what can be predicted by the linear theory, and in particular, he conjectured that the tallest member in the Stokes wave family will be distinguished by a sharp cusp at the wave crest with a continued angle of 120 degrees, famous picture. Now, Levi-Chibira and independently Nekrasov in 1920s, they constructed these waves of small amplitude, and the large amplitude theory came by Krasovsky and Kiri and Norbury with the degree theory and the global bifurcation theorem. And the highlight of this story is that Amy, Frankel, and Toland analytically confirmed the Stokes conjecture about this highest wave. Now, Toland and his collaborators in the early 2000s, they came back to this Stokes wave existence theory, now using the Babenco's equation, which I recorded in the box. This equation is non-local because it involves the Hilbert transform, the script H. Now, in the irrotational case, so for the potential flow problem, the typical way to do is we rewrite the problem entirely in terms of the quantity that is defined only at the surface, so to avoid the free surface issue. Now, insisting on this economy of the unknown, we have to pay a price, and the resulting system typically is non-local, and the Babenco's equation is an example of it. And lastly, following the work by Konstantin and Strauss, now there are a lot of works done for the Stokes waves, including the effects of vorticity, representation, density stratification, and many others. So in this, theoretically, these waves do seem to exist. However, in the 1960s, Benjamin tried to create these waves in the experimental setting, and he couldn't, so he concluded that these waves would be unstable. And now the photos on the left column, I hope it's clear. They are again taken from this Van Dijk's book, and these photos taken by Beer. And now I'll explain the experiment. Benjamin went to this fluid lab, which I assume is nearby.
It used to be nearby, but it's
not
longer
anymore.
existence. They had to destroy the evidence.
I was so excited to show this picture in this location, but okay, but still close,
they
right?
did some of the experiments here and some at the National Physical Laboratory.
Okay, but he did when he did the experiment, it's nearby here, right? Okay, good. So now in this experiment, so he had this long water tank, and on one hand, he generated these nice Stokes wave patterns that travel downstream. That's the photo on top. And now he perturbed these waves so that the period or the frequency of this wave changes slightly. And then send them downstream. And now, after it traveled a very long distance, you see the photo at the bottom, and you can say that these waves got destroyed. Right? And to destroy this nice pattern, you don't have to put a huge amount of energy. You just change the period a little bit, and you can accomplish this. Right. Shortly afterward, Benjamin-Feir provided a theoretical explanation of their finding, and almost the same time, Quidam, he developed his theory of nonlinear dispersion, and he applied his theory to the water-wave problem and the so-called modulational equations of Quidam's sense. They changed their characteristics from hyperbolic to elliptic if the wave number of the underlying wave and 1 times the undisturbed water depth, if this number is bigger than a critical number, which approximately is 1.363, so that these waves are unstable. And we call this phenomenon now Benjamin-Feir or modulational instability. And Zakharov and Ostrovsky, they wrote a very nice article about the early history of modulation instability. I was reading that article and I found that Quidam, initially, he was puzzled by his finding when these equations change in characteristics. And then after he learned about the works of Benjamin, its penny dropped. Another interesting historical aspect of this, supporting results came almost at the same time, but independently by many people like Lighthill, Benjamin-Feir, and Ostrovsky, Zakharov, and again quoting this Zakharov, Ostrovsky, the idea was emerging when the time was ripe. Modulation instability is everywhere, and it's a fundamental mechanism of instability in many physical systems, and it's related to many nonlinear processes like an envelope soliton or dispersive shocks or thick waves. Now, very recently, there are a lot of work trying to translate these formal modulation theories by Benjamin-Feir or Quidam into rigorous mathematical results. And I listed here some of the references devoted to that. Bridges and Milke, in 1995, they proved the Benjamin-Feir instability for Stokes waves to the exact water wave problem. But in the finite depth case, yes.
Can I just comment on what we actually did do? It's not as strong as what you write there. All we proved was the existence of at least one unstable eigenvalue.
Yes, but that's enough, right? To say it's unstable.
Yes, that's right. But it is true. It breaks down infinite depth.
Yes, but the proof sadly breaks down in the infinite depth case. And in my understanding, which is not your understanding in your paper, is I try. No, like there are many places that for example, the flux is not defined and things like that. But I think the fundamental issue here is okay. So you guys now map this water domain that's bounded by free surface and the finite bottom into a channel, right? And then now, if you apply a Floquet theory, then the things boils down to that you're studying the eigenvalue problem spectrum of some operator that is defined in the box where the edges are identified. Okay, then, well, clearly the spectrums are like a discrete eigenvalue of the spectrum is. Now, if we exercise this in the infinite depth case, then we can map it in an unbounded domain now, and well, we have an essential spectrum which we don't know how to deal with. Okay. On the other hand, a popular exercise in this business, and this the irrotational case is, well, we can always write the system in terms of only the quantities only defined only at the surface. So we can avoid this unboundedness of a physical space, which will create the essential spectrum. The price to pay is, well, we'll have to deal with non-local equations. So can I have it back?
I think you have to push the board down.
Oh,
Yeah.
smart. Okay. And I'm not, okay, I'm still here. So my idea towards this Benjamin-Feir instability is, how about we develop a modulation instability theory that works for non-local equations? And non-local equations are really a lot of places, so it's not a bad thing to have, right? Now, these works written in gray on on the nonlinear equations or generalized KDB equations, they are based on the Evans function techniques or PDE methods. And when we have a non-local equations, then they are no longer applicable. So the goal of this project, in other words, is to find a replacement substitute of the ODE methods and still conclude modulation instability. Right? Now, I'm going to explain a recent work that I did with Zerbronsky, and as the title suggests, we're using the variation structure to replace ODE techniques. All right, our theory applies for a very general class of Hamiltonian systems, but to illustrate today, I'm going to focus only for the equation in the box that I labeled star. Okay, this equation, the script M is a Fourier multiplier, and its symbol is, I'm denoting by little m. And if you look at the linear part of the equation, then it's a dispersive, and this little m is the phase speed of the simple harmonics with wave number c. So it combines this dispersive effect and the simple power law nonlinearity. Right. Perhaps the best known equation in this star family is the KDB equation, the original one, for which the symbol little m is a square function. But this equation star is non-local unless my symbol is a polynomial of IC. Examples are the Benjamin-Feir equation and the ILW equation. Another interesting example proposed by Woodham in his famous book on linear and nonlinear waves is to take my symbol to be the dispersion relation of the exact water waves. Right? Now, well, if waves are long compared to the depth, shallow water regime, so that the d times c is sufficiently small, then we can expand this symbol in the order of dc. And if you look at the quadratic part, the first two terms, that gives the dispersion relation of the KDB. So KDB, we can view this situation as the KDB equation approximates the dispersion of the Woodham equation up to second order. Woodham was interested in breaking of water waves. And now, on one hand, for shallow water equations, they develop shocks, right? And these shocks are relevant to what happens to the wave breaking in water. But shallow water wave equations, for the shallow water equations, all solutions break down. And that's not true what happens in the real world. On the other hand, KDB equations, solutions never break down. So to compromise these two, we then propose this equation and claimed that this equation captures the phenomenon of wave breaking. But this equation can explain many other aspects of water waves, and we'll see it later in this talk. As I said, we're going to use variation structure of the equation. So I'm going to note here that this equation has three conserved quantities that can be interpreted as the Hamiltonian, the momentum, and the mass. All right, we need to have a periodic traveling wave to study the stability of. So let's assume that there is a solution. And we're going to assume that the solution is even to break the symmetry. And it depends on four parameters. C is the wave speed, and T is the period, and X0 is the spatial translate, and A is the constant of integration that appears when we integrate the equation.
I have a question about your definition of whether something is local or non-local. I mean, the finite depth problem here.
Yeah.
If it's viewed as a problem in x and t, it's non-local. If it's viewed as a problem in x, y, and t, it's local.
Right.
So it's just a matter of what.
Yeah. No, your definition is my definition.
Okay.
Okay. And where was that? Okay. And alternatively, periodic traveling wave is a critical point of the modified Hamiltonian E, which is H minus EP times AM. When we're given a specific equation, of course, course, we'll have to prove the existence. And I'm going to say that for a very large class of dispersion symbols M, we can construct solutions using variation argument. In the worst case, we can use the mountain pass theorem. Now, in the special case, when the dispersion operator is a fractional Laplacian with the power alpha bigger than 1/3, so that the equation is energy subcritical, then we can construct a local minimizer of the Hamiltonian subject to the conservation of the mass and the momentum, and they serve a periodic traveling wave. Now, with the equation, I'm going to explain with this solution. I'm going to explain the notion of instability I'm adapting. First, set this equation in the moving frame with speed c, and linearize the equation around my periodic traveling wave u, and look for the solution which depends exponentially in time. Then you get this eigenvalue problem for the linearized operator I call script L. And we say U is spectrally unstable if the L2 spectrum of this linearized operator is not contained in the imaginary axis. Well, if we find an eigenvalue whose real part is not 0, then because of symmetry of this equation, we must be able to find an eigenvalue with positive real part. That means the solution to this linearized equation grows exponentially in time. So that's the instability I'm talking about. And the point here is the perturbation function V doesn't have to be T periodic. Okay, so we're not perturbing the solution with the same period. Now, for the user PDEs, before that, typically this spectrum in L2 contains essential spectrum. And that's the first source of difficulty. Now, for the user KDBs, user PDEs like a KDB equation, now one can relate this essential spectrum to the eigenvalues of the monodrom map or the periodic Evans function, so you have a very good understanding of the spectrum. Question?
What was x0 on the previous slide? You said spatial
x0 is, well, the equation is transdirectional invariant in the x direction. So you can just locate the origin anywhere, and that's my x naught. And it plays almost no role in the analysis.
You picked it where it's even though, right?
Yeah. Okay. So like once I pick this x naught, then my solution is even with respect to the wave crest.
Got it.
Yep. Okay. Now, so in the local case, we can use most of the time the Evans function technique. For non-local equations, instead, we just use flow-path theory, and we decompose this spectrum into a family of spectrum in the periodic L2 function of modulated operator L tau, and L tau is defined in the box down there. The good news is the periodic spectrum of L tau is made up of discrete eigenvalues. So by this decomposition, we are decomposing this essential spectrum into a one-parameter family of discrete eigenvalues. Okay. Let's see. It would be nice if we know completely the spectrum of L tau for any tau. Okay. But unfortunately, it seems impossible, except for very few special cases. For example, if the equation is completely integrable. But searching for instability, we only need to find an unstable eigenvalue for some tau. Right? So I'm going to look for only for unstable eigenvalue near the origin for small tau. Okay? My strategy is, first I'm going to study the spectrum of unmodulated operator L at the origin, and then I'm going to see when I increase tau, how this spectrum bifurcates. Okay. So step 1, when tau is 0, under the assumptions, these 3 assumptions, I can prove that 0 is the eigenvalue of my linearized operator with algebraic multiplicity 3 and geometric multiplicity 2. And the basis and the dual basis of the corner space can be computed using variational structure of the equation. Again, when you're given a specific equation, you have to verify these three conditions, right? And the most serious one is the second one, where by definition, ux is in the corner of my linearized operator. But this requires that ux is the only one in the corner. And this is not true sometimes. For the KDB type equations, you can prove this property using Sturm oscillation theorem. And for the fractional Laplacian, Frank and Lanzmann developed a replacement of oscillation theorem, and they proved this property for the solitary wave case. And with a little modification, we can have this property for the periodic case. So in some cases, this can be verified. All right, now if you have three eigenvalues sitting at the origin when tau is 0, now we're varying tau, and we will simply expand our modulated operator L tau in kind of a Taylor fashion, right? Then the coefficient operators are made of the commutators against x, and this function x is not periodic. But these commutators are periodic, so this expansion is well defined. And it can be computed in the special cases. And then I'm going to expand my eigenvalue mu and eigenfunction phi in terms of tau. And there's no mu0 because I'm expanding mu0. Right? And throw these to the eigenvalue problem. And after long calculation, the conclusion is we'll have a complex mu1 if this 3×3 matrix that I call the effective dispersion matrix has a complex eigenvalue. Now, if my mu1 is complex, then, well, since mu1 is multiplied by I, this will make an unstable eigenvalue. Okay? And now, these entries of this matrix D is defined by the L2 inner product of the basis of the corner and dual basis and these coefficient operators that I get when I expand L tau. All right. The conclusion, in other words, is so my underlying wave is going to be modulationally unstable if the discriminant of this cubic polynomial, whose coefficients are defined like this, is negative. Okay? So that's our main theorem. And in principle, these coefficients can be expressed in terms of the kinetic and potential energies and the momentum and mass as functions of the parameters of the steady wave equations, so CAT. Right? And now, if you look a little bit closer, then these coefficients involve L0 inverse, right? And these may not be computable, but we have a positive identity that helps to compute this. So we never have to invert this directly. Questions at this point? Yes.
Can I ask you something? As far as I remember, this is a Hamiltonian system, Lagrangian. The system is almost invariant to shift.
Invariant
so
to shift.
You have three roots, yeah? You have
right.
three roots at the origin. According to me, one of them should be the shift.
Yes.
Oh,
yes, yes.
And then the other two, I mean, but if you realize
so
that, you
that's
can eliminate
V2.
that, yeah?
That's V2. That's generated by the translation invariance.
But then you can eliminate that and just look at the other two. Because then the problem is much simpler, yeah? You just have 2 by 2.
Sure, but this isn't, I don't think it reduces the computation that much.
I would think so.
You think so?
Put it another way, don't you have a zero eigenvalue of your polynomial in your next slide?
Yeah, so
That's
D, in your expansion you had a constant that should be 0. Next slide.
Next slide.
Yeah.
After that.
After that.
Oh, okay.
So D0 should be 0.
D0 should be 0. Oh.
Unless you've already factored out the zero eigenvalue.
So if because it's a trivial, right? In the X
Yeah,
naught.
yeah. That's just a guess. I mean, it's also very hot, so maybe I'm confused.
I'll do the calculation after this talk. I'll do
Yeah.
the calculation. Question.
Actually, I've got a follow-up question to that. So
Mhm.
with the three eigenvalues at the origin, because of the symmetry,
Mm-hmm.
one of them I think has to stay put, and then the others either have to go
That's
this way
exactly.
or this way.
Right.
Yeah.
You're interested in the case when they go
This way. Yes.
which means that you're really interested in the case of not complex roots but purely imaginary roots.
Yeah, but
Because this is long way.
Because
Mhm.
if they're complex, you can't maintain the symmetry.
Yeah, yeah, but you have, this is a proof, yeah? You can't
yeah,
assume.
but then in this framework, it's because I'm taking out the I already, so
Right,
you know,
right. So
it's
that's why you would have.
Sure.
That's why you would get pure imaginary.
yes, yeah, we
But
don't
it
know
would
like
also make your polynomial simpler again. I think.
These are very good comments because as I'm going to, I was about to comment that how complicated this formula is.
Yeah, I was worried as well.
Yeah.
It can't be
Question.
that.
So you have all these inner products.
Yep.
Should I interpret those as the quartet coefficients that I would normally use to predict the Benjamin-Feir instability? Quartet interaction. So the four guys interact. Yeah.
I think at some level, very fundamental, this must be related to these four-wave interactions, and I don't have a direct route between these two. At the KDB level, there is some work done to justify this Withams calculation using this modern approach. And at this level, I don't see things yet that clearly. All right, and as we all share, now in this current form, my modulation instability index seems daunting, truly. But I want to comment that there is a previous work done by Jared and Matt and for the KDB equation, and their index is as complicated as this, almost. So I thought this is the way it should be.
What do you mean by index here?
Index is the discriminant of this cubic polynomial, right?
Okay.
That if that is negative, then you get instability.
Oh, right.
Yeah. Question?
How to reconcile your approach with the earlier books by Lighthill and Witten, so who just wrote, so you have a system, if you have explicit, or implicit expressions for your stationary wave, you could write relational equations, and whether the system goes elliptic or becomes hyperbolic, it tells you immediately about stability, instability, at least in the long wave limit you are considering.
Right.
So what's the additional gain for your pain?
What is the additional
First of all,
gain?
this is not water waves.
No. So for anything. So if as long as you have expression for stationary wave.
Okay, but you have to be a little bit careful though, because you're arguing on behalf of Witten theory in infinite depth, where there's just a very simple Lighthill criterion.
No,
She's closer to
not at all.
Let me answer this because the
Okay.
question is to me.
The answer was
Yes.
the question
So
of the speaker,
to answer to the question, what we try to do is we view somehow these earlier works of Witten or Benjamin-Feir somehow former. And what we try to do here is try to provide some mathematical rigorous background to it. And so we're not gaining maybe too much, more than what we done. Actually, because we really like using strict analysis, our conclusions are much weaker than what you can calculate just by taking this slow modulation and deriving modulation equations. Those former calculations get you very quick answer very painlessly. And but what we do is it is nice to provide some rigorous mathematical background like what Bridges and Mirke did.
Okay, then my next question.
Yeah.
Where is the hole in the foundation of Witten's modulation?
Yeah, so
What
can
is
you find an example that your
There's
theory
no
says
hole.
is unstable?
There's no
And
hole.
you, with the modulation,
There's
you
no
can't
hole
tell?
I
There's
can-
no hole, listen.
No hole.
Oh, you
I,
listen to
I don't think there is a hole, and I really respect these all your works, and I'm just saying that these derivations are just saying like if you expand and you don't really kind of justify in if you're a pure mathematician, then you may not like this as a proof. So it's like, am I making myself clear
One is
here?
necessary.
Yeah. So like I'm wearing like a pure mathematician hat. I try to make a proof. Say.
Yeah. No,
And
that's fine.
well, so like my definition of proof is maybe more
Yeah,
rigorous
okay,
than
yeah,
your definition of.
But that's fine. But you have to use the background of Hamiltonian, because then we know that
Oh yes.
that you just get
Sure.
instability if to go.
Yeah, this
together. So
this
if
of
you
course it very heavily relies on the Hamiltonian because we're now like giving up the ODE method, right? We must have something, right? And now like I'm presenting here, if we now take a Hamiltonian structure when we give up the ODE method, then what we can do. That's what I try to do here. Oof. Okay. So now it's going to be not so exciting, but well, this because there is a possibility to make this instability simpler, but nonetheless, this is what we have today. So let me proceed from here, and I try to persuade you that this is not totally useless. So, example one. So, as you noticed, well, I've been trying to writing down the things more specifically for fractional Laplacians throughout my presentation. So, take this dispersion symbol to be dispersion operator to be fractional Laplacian. In this case, the equation has a scaling invariance, and that reduces the form of this matrix T a little bit simpler. But not as much as you'd like, because these 1, 2, and 3, 2 entries, they are still very complicated.
So when you say scaling invariance, do you mean of the equation governing?
Equation, yes, the
traveling waves.
time evolution equation.
Okay.
Yeah, itself has a scaling invariance. And here, I am writing down explicitly these inner products in terms of, as I said, the kinetic and potential energies and momentum and mass as a function of CAT. So this can be really done. All right. Well, if we look at the Benjamin-Feir equation, which is when alpha is 1, then we have Benjamin has written down this explicit solution, explicit form of the periodic traveling wave. And using that, you just calculate these integrals. And then, well, see, the matrix D is not that bad. Right? And you can easily calculate that this has 3 real eigenvalues. So the periodic traveling waves for the Benjamin-Feir equations are modulationally stable, and even distance nu. And yes, if it is not formal.
Yeah.
What?
You see, it's impossible. You have 3 eigenvalues.
Yeah.
I mean, I'm trying to get rid of it's a bit strange.
Yeah, so if really like we can reduce this to quadratic polynomial, then I guess this should go away, but I sit down and write tonight. I'll try.
Yeah, you can take your time.
Okay. Yeah, maybe I can really finish the calculation tonight. Okay.
Yeah, so but it must be a trivial thing.
All right.
You must be able to
Now,
isolate.
So,
yes, the two
well, this matrix D, if we don't have explicit solutions, still it's kind of impossible to calculate, right? But and yes, these are very well suited to numerical calculations. Okay? So I ran a very simple numerical experiment, and neither Jared and I are serious numerical people, so we just ran some very simple iteration scheme to Mathematica. We're not fancy people here. So first, let's take the KDB equation, and we just ran a very simple-minded iteration to generate a more numerical solution, and we compare that to known colloidal wave solution, and our numerical solution and the analytic solution matches up to the order of 10 to the minus 12. So they're in good agreement. And then we calculate this matrix D, and now they have 3 eigenvalues real. So the solution is modulated stable, which is a known fact, right? So we just say here that we recovered the known fact. And now we took the Benjamin-Feir equation, again, repeat the process. And this matrix is, if we evaluate these with CAT, then it matches pretty well with the analytic matrix. And again, we get modulation stability. And then we went on a little further and fix these parameters, the CAT, and vary the alpha, the strength of the dispersion, from 1 to 2. So we look at the family of Benjamin-Feir to KDB, right? In the previous slide, I told you that Benjamin-Feir and KDB, they are modulation stable, right? But then interestingly, we found an unstable solution for alpha value near 1.025. And the picture on the right is the profile, this unstable profile. And this seems strange because I'm going to explain in the next slide another way to use this theory. Well, if you're looking at the small amplitude solutions, then you can expand your solution in the statics of small amplitude parameter, and you can calculate everything explicitly. And for small amplitude calculation, tells you that this fractional Laplacian equation, the solutions are mostly unstable only when alpha is less than 1. But this wave is not that small, so it doesn't directly contradict, but still it's hard to believe. Another way to look at this strange phenomenon is that, well, in this family of nonlinear dispersive equation, well, we can play on one hand the dispersion, the strength of dispersion, right? So we can vary alpha, or we can vary the strength of nonlinearity, varying the power of the nonlinearity, right? And in these two families of equations, right, they are going to be L2 critical, and L2 is the momentum. When alpha is 1/2 for the first equation, and when P is 4 and the second equation, and this is the borderline of the stability of solid waves. Okay? And now, these equations are mass critical if the first equation is, if the alpha is 1 for the first equation and P is 2 for the second equation, and the mass is almost L1 norm. And now, these mass critical exponents are the borderline of we want to say is borderline of the modulation instability. And it is in the generalized KDB case. MKDB has unstable solution, and if P is less than 2, then things are stable. But it doesn't fit into this. Doesn't fit into this fractional Laplacian equation if this truly exists. Well, one possible thing is our iteration scheme is really not sophisticated, and maybe it converges only when the solution is stable, or I don't know. And I would like to have some help from some sophisticated numerical people to really see this is happening, or this is our weakness of the numerics. I don't know.
So you try to minimize alpha, is that right?
Minimize. We just want to. No, we just want to see like what happens if we vary alpha, because we start from stable and we're ending at stable, and solutions are stable all the way through, or like there is a transition instability. We just was playing around.
But I mean, if you wanted to go down to say alpha equals to 1, right? There may be some other
Oh,
parameters.
if alpha is below 1, then we believe that the solutions are unstable.
Sure.
And what's strange here, I thought, is alpha is bigger than 1, yet it's unstable. That's something that I don't have a good explanation to.
You don't have
Uh-huh.
any proof.
No,
It's
this isn't.
unstable if alpha is below 1.
For small amplitude, we do have proof, but it's only for small amplitude.
When you say a proof, you mean that there exists a value of alpha at which, like a
No, the statement is for alphas less than 1,
Yeah.
or small amplitude traveling wave solution or modulation unstable.
What does it mean unstable?
Modulation unstable. So it means if you perturb, so that the perturbed solution.
No. You start with some linear self-adjoint operator, yes?
No. I'm talking about at the level of PDE, or like the evolution equation. Okay.
Evolution equation, yes.
So the evolution equation has the periodic traveling wave. All right.
Yes.
And now, well, I compare this to another solution which is close, right? That's the notion of stability. And my comparing solution has a period slightly different from this steady wave.
Yes, but
Okay, and these two, they
it's
don't.
a spectral instability or not?
Yeah, it's a spectral instability. Yes.
It's a spectral
Yes,
instability.
this solution is spectrally
Therefore,
unstable.
you use a spectral analysis, yes?
Yes.
Therefore, you consider the operator on the L2 of R on the
Uh-huh.
control line.
Yeah.
Yes.
Yes.
Next, you represent your spectrum as a union of the spectra of Bloch operators. LT,
Right.
Yes.
Yes.
How many T, for each T, you have to find the number of spectrum of operator LT which has non-zero real parts, yes? You take LT, looking, each has the discrete spectrum, yes?
Yes.
You're looking for one eigenvalue
Right. For
which
one.
which has non-zero real part, yes?
Yes.
How many T you can examine?
How many tau, right? The Floquet exponent. Well.
The question is, because if you prove this fact only for one T, for spectral stability on the real line is give nothing, because wave package is some integral with respect of this.
Let me say that these spectrums, they are continuously dependent. They depend continuously on this Floquet exponent tau, right? So what I prove is for a small interval of tau, right?
Yes.
We have unstable eigenvalue.
Yes, it is rigorous proof of this.
Yes. Does that settle your question?
For small amplitude.
All right. I have another kind of topic. So, and I'm running out of time. So let me. This was fun. It's a lot of questions, but okay. As I said, well, for general dispersion operators, then well, we don't have a good idea about what the solution is for the steady wave equation, and these are not so practically useful. But at least for small amplitude, the things are explicit, and we can say things. So Matt and I took the Woodham equation, if you still remember what it is. So the dispersion symbol is now describing the dispersion of the exact water waves, right? And here in this scripts, we wrote down the small amplitude solutions, and A is the smallness of the amplitude, all right? And for this case, we can analyze the spectrum completely, but let me just jump into that. So if we perform this perturbation analysis using this explicit form of the solution, then we're landing at the modulation instability index, which may look a little complicated to you. But anyways, so the underlying wave is going to be modulated unstable if this quantity is negative. And now there are 3 factors in the numerator and one in the bottom, and the first 2 in the numerator and 1 in the bottom are always positive for the with ensemble. And the last one in the numerator changes sign only once, and this we have to inspect by pneumatics. This function is complicated. All right, but there is only one 0, and that 0 is near 1.146. So our conclusion is that the period at small amplitude, period traveling wave to the Witham equation is modulation unstable if the wave number is bigger than this critical number. So it needs to be qualitatively recover what Witham and Benjamin-Feir did in the early 1960s in Custom. Yeah.
So it is strange that your instability domain is kind of in the domain of larger wave numbers, because usually the modulation instability it is between 0 and some large fixed number. So
well, if you look at this light criterion, then fix the depths, then you have to have short waves to have the instability.
Yeah.
Long waves like a KDB, so they are may not be
no. I misunderstood. I thought that it's about modulation of wavelengths. No. Okay,
Are we good?
I understand now. Yeah.
Okay.
I know what you're
Good.
about.
All right. Now, and then, so, the Witham idea, we got interested in this Witham equation. The recipe, basically, for the Witham equation is combine this dispersion relation and quaternonlinearity, right? So, we went on adding surface tension effect and vorticity. Now, if the surface tension is acted on, then the dispersion relation becomes this. So it's multiplied by square root 1 plus t c, and sorry for the abusive notation, but t is the strength of the surface tension. And we're assuming that m kappa is not equal to m of 2 kappa. If this realizes, then at the existence level of steady waves, there is a resonance. So you have also put return ripple. And I do think the analysis is possible, but I expect that we have to deal with 5 by 5 matrix, and we're not there yet. And we think, in fact, it is better to do this numerically. Anyways, now, well, here's something that I want to say. With the surface tension, dispersion relation behaves differently. So when the strength is substituted for less than 1/3, then kappa times m kappa, well, this goes here, versus kappa, but there is a minimum, okay? And when tau t is bigger than 1/3, then the dispersion relation is monotone, all right? And the reason I'm saying that is if you go back to this instability index, then the first term, by the way, this m, the derivative of kappa m kappa is the group velocity, okay? And m at 0 is the long wave limit of the space speed. And so now what I can say is, well, the stability and instability change each and every time one of these factors vanishes, right? And the first factor can vanish when, when the surface tension effect is less than 1/3, then all these guys can vanish, right? And now, if the first factor vanishes, and you don't remember what the first factor, but the first factor vanishes when the group velocity takes the minimum. Okay? And the second factor vanishes. Let me just quickly put it on. If the group velocity is equal to the long wave limit of phase speed. And the third factor is the Benjamin-Feir type thing. And the last factor vanishes when, well, the fundamental harmonics interact with the second fundamental harmonics, right? Okay, so these can happen when t is less than 1/3, so you have this shape of the dispersion relation. So what I can say is if you add a little bit of surface tension, then you have a suddenly see all like very rich like resonance phenomena that contributes stability and instability. All right, and when T is bigger than 1/3, then things are boring, right? So we have qualitatively the same conclusion as the gravity Vidam equation, and we plotted this stability diagram, and it's strange that we did this for the kappa and the kappa times square root T plane. The reason is we want to compare our result to the old literature done by Kawahara and Redekop in the 70s based on the nonlinear Schrödinger equation. Okay, this is another way to go forward. Well, our picture recovers their picture almost, except the upper left curve. This upper left curve, if you look at these old literatures, then it's just well, it doesn't have this dip. Except that we recovered the old former literature completely, and this curve. Sorry about the bad notation. This gamma is I3, and this is well. So there are 4 factors here, right? And I1, I2, I4, they are all determined at the linear level. It uses only m. Okay? So you can read off from the dispersion relation. And I3 is more complicated. And this is actually what the nonlinearity contributes. And we have 2 questions. Yes?
I'm confused by your assumption on avoiding Milton ripples. The one that you wrote down is just one of infinitely many that you have to avoid. Right? You also have to avoid m of kappa is when you go to m of 3 kappa and 17 kappa and whatever you want.
The NLS coefficient doesn't know about those. That's why she doesn't.
Oh, because
No, like yes, as long as well, and it's also clear at the expansion. So if m kappa is not m2 kappa, then this expansion works.
You're stopping at second order.
Yeah.
Okay.
No, but at next order, what he's saying is you get m of 3 kappa.
Right.
But this is enough to conclude the instability. And in fact, if we use small amplitude calculations, we go 1 order smaller than this abstract variation approach. But maybe it's too much to say here. Anyways, what I want to say is, well, so the only thing that we cannot recover from these is this first curve, which the nonlinearity contributes. So we think this Widom nonlinearity is not good enough to recover the full picture when the surface tension is added on. And I think it's interesting to find the correct nonlinearity that can predict this correctly. And lastly, if we add the vorticity, well, for arbitrary vorticity, you can calculate the dispersion relation, but it cannot be solved explicitly. So we just look at the constant vorticity, and this, again, qualitatively gives the same answer as the zero vorticity case. The only thing that I want to remark is for negative vorticity, then this critical wave number is decreasing as we increase the magnitude. So it reaches instability very quickly. And for positive vorticity, it does the other way around. So the negative vorticity drives instability, and I think it is somehow reminiscent of these extreme waves with constant vorticity. But I stop here. Thank you. Yes.
So I don't think it's surprising that you don't recover that top curve, because
okay.
So they do NLS, which includes cubic terms from full water waves, and you did so Redekop, for example, did that, and you've done a quadratic model, so it should be different when you consider the nonlinear stuff.
But that's what she said.
Yeah. So you shouldn't be able to match it.
Yeah, but then well, do we have some correct nonlinear? Can you think of heuristically like a correct nonlinear?
Well, not in a one-way model, you shouldn't be able to get cubic terms correctly.
Well, you can get the coefficient correct.
Well, yeah, you can get the coefficient correct. Yeah.
But
so then you can look at the Akers-Milewski equation.
Yeah, but say like 4 out of 5. I think it's not too bad. Well. And this is a cheap calculation, right? So. Yes.
Where did you use the hypothesis N3?
N3. Oh. Well.
Because you never actually used those derivatives anywhere, I see.
No, N3, where it's hidden, right? N3 I call G, right?
Yeah,
And there are lots of G inverse hanging around.
Oh, is that where it comes in?
Yeah, so if G is 0, then this becomes degenerate.
So you don't need that for the existence of the traveling waves, only in the stability theory.
I don't understand your question.
Well, you have two parts to your story, right? You have to show the existence of the traveling waves, and then you study the stability of the traveling waves. So you don't need G not equal 0 for the existence of the traveling waves,
Correct.
only in the stability theory.
Correct.
Okay.
Yeah. But then if G vanishes, then I think there's a modification. Then we just have to calculate the dimension, co-dimension thing, and things are slightly more complicated. I think it is doable in principle, and I tried some time ago against the KDB and didn't get the result. So
It should be non-zero for KDB.
no, there is actually there is the co-dimension 1, if I remember correctly, subset of the solution manifold where G is 0. I hope I'm remembering correctly, but it's a long time ago.
Further questions? Then thanks once again.
Thank you.